It's hard not to smile. Joey's watching me. Hi, math people. Happy May Day tomorrow. Lesson 85 today, though. Or, well, you'll probably watch this on Friday. Maybe. Okay, finding polynomial roots, part 2. It's the sequel to end all sequels. Yeah, all right. So today, actually, we're going to talk about some more factoring. I feel like I've talked about this before. So maybe it would be like, why is he doing this? Maybe a substitution trick that I've shown you before. Yeah, pretty much. It's, oh wait, there's more. Cubic equations, polyroot finder. Okay. All right. This won't be so bad. Kind of like getting shot. You know, it'll be painful for a moment, but then it'll be all over, and then you get a lollipop. Righty then. The warm-up, one of the warm-up problems, I guess, in the thing, has a 16x to the fourth minus 81. Okay, 16x to the fourth minus 81, and it's asking like, what would you do there to factor that problem down? Now it's a little different because it's got an x to the fourth in it, but everything else, the 16 and the 81 are both square numbers. So can we write this as something squared minus something squared and have the difference of two squares? Yes, we can. We've got 4 squared and we've got x squared squared. So little trick there that we're going to see when we get even number powers, we can always, even numbers are something that every divisible by 2, all of them are, so we can rewrite them and we can do some factoring. Anyway, there's our difference of 2 squares. We can break that down into 4x squared minus 9 and 4x squared plus 9, and then we got the difference of 2 squares there again. I think we dealt with a problem like that in a previous lesson. So factor it one more time. This is 2x squared minus 3 squared, or 2x minus 3, 2x plus 3, and then this carries on down, 4x squared plus 9. Now, if we have to have real numbers, then we can't break this down anymore because this is the sum of 2 squares, and we can only do that if we're going to use complex conjugates. So anyway, we're finding roots. I don't think we're looking for complex roots today, but we'll talk about that briefly. I think then the next section here, the next thing is a bit of review, and that is when we get cubic polynomials. When we get something that's x cubed, and we're looking for ones that are either the sum or the difference of cubes, and there are factoring forms for those. Joy, just raise your hand if you need to ask a question. No, you're good. All right, I got a thumbs up, man. I got a brown thumbs up, skin tone thumbs up. I can't do that on my phone. It won't let me change the skin tone of the thumbs. My kids are like, "Hey, look, see," and then they go here, and they go, "No, it doesn't do it." Well, there we are. Dumb phone, dumb emoticons. Where are we? Oh yeah. These patterns are shortcuts, right? So they help us pull the thing apart and like do something with it, where otherwise really you have no clue how we're going to pull these things apart and do anything with them. So let's look first at the sum of cubes. That would be this. If I can write something as x cubed plus a cubed, then I can break it down like this. I can always factor out the x and the a, and then I'm left with x squared business, except now it's minus a times x plus a squared. That's the important part right there. The signs alternate between plus, minus, plus. Okay, sum of cubes. All right, the other one is the difference of 2 cubes. And the factor form there is you can always factor out an x minus a, and then all the things over here are positive. plus, 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 positive, positive, positive. Okay, so if I factor out a plus, I have a minus in there. If I factor in a minus, they're all pluses. And the pattern can continue with things of odd powers and even powers. There's patterns on your algebra sheet. If you look right here on it, you've got your common factoring examples. And if we go down to, we get some cubed things here. There's x plus a cubed, and then there's x cubed plus a cubed, and x cubed minus a cubed, and x to the 2n minus a to the 2n, which we'll look at that one as well. So this is the last three on that factoring, those factoring forms that we're looking at today. Okay, so let me show you, I'll show you two here, one of each of these, sums of cubes and the difference of cubes. Difference of two cubes, dot, doesn't really go, does it? Whatever. Here we have an example, x cubed plus 64. And then I'll give you another one. We'll have x cubed minus 27. So you got to recognize, or you got to figure out, 64 is something cubed in order to see if this is the sum of cubes. So we want to rewrite this as x cubed plus something cubed, and that something is 4. So we're going to use this, and we're going to plug it into this form, and it says that we could break this down to x plus 4, and then x squared minus 4x plus 4 squared is 16, and we've got ourselves factored. All right? Now that's nice. Okay, so right now we're just factoring. We're just breaking it down. We still haven't found roots, right? We haven't found roots yet, but we will. Our other form here, x cubed minus 27, again, we got x cubed minus, and this time it's 3 cubes. 3 times 3 times 3 is 27. So this rule says we can go x minus 3, and then have x squared plus 3x plus 9 as our factored form. Again, we haven't found the zeros or the roots, but we have found how to break this down. And the only thing that we would change if we're looking for roots is that the equation would be equals 0. We're going to use the zero product property to go after the other ones. So what if that's the case? Now let's talk about roots. Okay, we have this times this equals 0. So either x plus 4 could equal 0, or this business could equal 0, right? And so we'd split it up that way. And here, we obviously tells us that x equals negative 4. And then if we take this part here, well, we're going to use our polynomial root finder, or we're going to use the quadratic equation, or we're going to complete the square, but we're going to find those other ones. They might be complex conjugates, or they might be things with square roots in them, but we're going to be able to find it because at that point we're left with quadratics. We've got lots of different skills for going after quadratic equations. Same thing on this one. We know that x is 3, and then there's 2 other answers here which might be complex conjugates. Might be one number with a multiplicity of 2, but it doesn't look like it, or it might be 2 real numbers. I think this one's complex conjugates, but you can use polynomial root finder at that point to find those other roots. Okay, now let's go after this last one down here, even number of powers. So, this is when we get something like x to the 6th minus 4. That is factorable. And the key here is that any even number is 2 times something. That is, any of them, if you've got something to the power of, you can always break it down to something squared. There's the 2 times something. And here, that something's going to have to be power rule 3. 3 times 2 is 6. So that's something squared. Right? Or if you need to, you can turn that around and you can have squared in here and the cubed out there, but we're talking about things that are even powers here. So let's focus on the fact that we can break it down to something squared. Okay, x to the 6th is this. X to the 10th could be rewritten as x to the 5th squared. I'm going to do a little substitution for you today. I think I've done this before in class. But let's start with this one. We know that we can rewrite this one as this squared minus this squared. Okay? Or even better, we can kind of write them in a similar fashion, though we don't need to. I could have written this as x cubed squared minus 2 cubed squared, because they're both to the 6th power. But really, all I need to do is write it as something squared minus something squared. And now I'm looking at the difference of two squares. So I would do this right here. Okay, difference of two squares would be this one minus and this one plus. Right? Does that look familiar? Difference of two squares. Now, I'm also looking at that this one is the difference of cubes. So this one is something cubed minus something cubed, and then so that can get broken down. This one can't unless we want to have, oh no, that's the sum of two cubes. So both of these then can be broken down again, right? This one here gets broken down to x minus 2 and then x squared plus 2x plus 4. And this one gets broken down into x plus 2, x squared plus 2x minus 2x plus 4. Okay, so we get this, 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 and this. Maybe these ones can be broken down again. Maybe you get complex conjugates. This looks like x, I don't know what else these things turn into. But I do get some more answers. X plus 2, x plus 2, yeah. Willie's mad. Okay, so I start getting some answers, especially if this is, I'm looking for roots. There's a 2 would work with this one, and a negative 2 would work for this one. And then these two pieces, we need to massage them a little bit and see if we can get some more roots that come out. Again, at that point, you can use a polynomial root finder or the quadratic equation, or you can do completing the square to see what the other ones are. You can also graph the original thing to see if you can see where the zeros happen to be. But that's using even number power rule to break it down into something that's simpler. If that doesn't look simple, let me show you what we do in calculus when you get to more complicated equations. You use substitution. So this would be kind of like a method you could use. And this method was used to figure out a general formula for cubic equations. Remember, we got the quadratic equation, there's a cubic equation, and the technique that they used to solve that was by substitution. So, for example, we've got x to the 9th plus 27 equals 0. This one has 9 answers to it. But how in the world do you factor something as disgusting as that? Well, it's something cubed, as this one is something cubed. And so we're looking at the sum of two cubes. And the sum of two cubes, the pattern, we just had it a little while ago. We're going to have x cubed plus 3, and then there's leftover stuff. That'll be x squared minus 3x plus 9, right? Okay, well, we still got this mess right here. There's 3 answers there, 4, 5. There's still like gobs of answers left over. Oh, actually, that right there is x cubed squared, and it's x cubed to the 1. So this even stays more complicated, right? And this is x to the 6th minus 3x cubed plus 9. So at this point, it looks like it's still way too much to try to tackle, because what do we do with x to the 6th minus 3x cubed plus 9? But right here, this is a quadratic form, because we've got something that's like squared here, an even number here, that's an odd number here. This is like, if this was x, this is 2x. We got x cubed, we got x to the 6th. This is x to the 6th is x cubed squared. So I'm going to go back to the beginning. I'm going to start there. I'm going to do a little substitution. I'm going to go right here and I'm going to say this is x cubed cubed, and then we got 3 cubed. We're going to take this out for right now. We're going to say x cubed equals, and then in math world they usually use substitution with the letter u. So we're going to, instead of using x cubed, we're going to use the letter u. Okay, so this is going to turn into u cubed plus 3. And it's just a variable, it's just a placeholder. And now it's the basic difference of 2 cubes. So this factors to u plus 3, and then u squared minus 3u plus 9. Now, this looks regular quadratic, not crazy quadratic, right? So we could go and do this as a normal quadratic equation. We can see if we can solve it, or we can plug stuff back in at this point. If I want to go and solve this, I can think of it like it's 1x squared minus 3x plus 9, and see if I can get solutions. And so let me pause, and I'll do that on my calculator. Did it. I didn't really do it on my calculator, but I did it using the quadratic equation, and I figured out that this part right here with, I guess I should say u, I get 1/2 plus or minus 1/2 times square root of 3. That's the exact answers. Now, if I go back and I'm going to replace that u with x cubed, this is where it gets a little like, oh no, what do we do? We get this. We get, oh no, actually that's x cubed equals that. So how do I solve for x? I take the cubed root of both sides, and I get this. And those are my answers. I get the cubed root of this plus, and I get the cubed root of this minus. And boy, the answers start to get really, really complicated, because we're talking about things with squares and 1/3 powers and 2/3 powers and stuff like that. Okay, so it can be broken down to a certain extent, right? It can be broken down to a certain extent. Even here, I would have to go back and I'd have to plug in x cubed again, replace the u with this. And now I'm looking at x cubed plus 3 equals 0, x cubed equals -3. I'm taking the cubed root of -3, right? I'm going to get some crazy answers. I'm going to get some complex answers. If I go and do polysmult, I'm supposed to really get 9 answers. I go to that one, polysmult, and it does allow me to go up to the 9th power, but it won't give me, it'll be a little tricky. So this problem starting off is 1x to the 9th, and then all the way down, and my last thing I get to put in is 27, and I solve it. It's thinking, and 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 I get this for answers. Now, some of them I actually do have up there on the board, but oh my word, there's like a bunch of complex. There's one real answer, and then there's 8 complex. There's 4 sets of complex conjugates. They don't ask you for that kind of stuff, do they, in the text? They're asking you to just kind of like factor the things and break them down and see, look for the real answers. Look for the real answers. Okay. So complex numbers, no, sorry, cubic equations tend to be a little bit more yucky. I should go online and find for you the cubic equation. I'll do that right now. I have it in a book. The cubic formula. It's like the quadratic. It's cubic. I'll post it before we're done. Okay, so example 3, solving cubic equations. 3x cubed minus 7x squared plus 4x minus 12 equals 0. Remember watching the Barry Mazer or whatever his name was on the cubics must have at least one real root, because all cubics do something like this. They start down here and they go up there, and so there has to be at least one place where they cross the axis. Do you remember that? So cubics must have at least one real root. If they have one real root, they have two complex conjugates, or they have three real answers, like something like going like this, 1, 2, 3, or maybe they'll have two like that, but we still get with a multiplicity of 2. So no matter what, there's got to be at least one. That's the moral of the story. And a graph would show it. I think on most of these types right here, your best bet is to graph it, and then use that Roman root finder thing. This one does give you one real and then two complex conjugates. And yeah, so try that one on a calculator. 3, -7, 4, -12 get thrown in there. That's really my main thing. If you don't get the picture that looks like they're in exact places, you're going to want to use your polynomial root finder. Example 4, I used my polynomial root finder, and I got some really nice numbers for that one. Okay, it was like 1x cubed plus 2x squared minus 1x minus 2 equals 0. And when I did that, I got my answers of -2, -1, and 1. And I bet you if you graph that one, it would look okay. Yep, it's pretty straightforward. I would take a really good guess. Come on. There, it's passed. That -1, -2, and +1 would be really good answers. You can ask it for the things, but it looks like it. It looks like it works really, really nicely. Another way to do it is graph it. See if you can find one of those that's right where you think it is, and then do some synthetic division on the rest of it to see what happens. So for instance, if you looked at this one, you're like, I think it's at 1. You double check and like, yes, one of the answers is 1. Then see what else is left by doing some synthetic division. Do that right? 3, -4, -4 times 1 is 4, 4, -4, 0, 0, 0. Yeah, so you're like, oh, yuck. Man, that wasn't too great. Okay, so maybe that wasn't a good idea. I just wasted like 3 minutes of your time. I would suggest trying that. The example 5 is a roller coaster design. I guess there's some game where you can do that even. And the roots tend to be the low points of the ride, and you can think about how long that would be in seconds, because they want to know how long is this ride going to be, when are going to be the low points, which are the high gravity and pressure points of the ride. How far along the ride are you going to get these? You don't want them to be too close to each other because you want to keep people waiting for more, right? Yeah. Okay, so use some factoring techniques. Please use some graphing capabilities on your calculators. Please, you can use some synthetic division, and you can use your polynomial root finder. Oh yeah, I said, and substitution. So there's several more options that you have for finding polynomial roots. Part 2. We're going to cover this stuff again when we get to pre-calc, so hopefully we're just introducing you to these ideas today, and you're going to get a little bit better at them as we go along. I think there's a reteaching for you that has some of these in it with some pictures and stuff too. Okay, that's long enough, and so you need some help. You know where you can find me.